Assalamu alaikum everyone. So welcome to lecture 13 in the 7th week of this course. So today we will wrap up our discussion on n-gram language modeling. N-gram language modeling was the first or most easiest way of modeling language as a sequence, and we use probability theory to model the the next word given the previous context. So we will discuss the various aspects of n-gram language modeling, including its evaluation and issues regarding its estimation. And I think that will be all for today. If we do have time, we might introduce the neural language model, which is the extension of this and more commonly used nowadays. So that is basically the agenda for today. All right, can you see my screen? Okay, so we were discussing n-gram language modeling, and this is basically a probabilistic language modeling. Probabilistic language modeling. So in this case, we model a sequence of words that may appear in a language by the probability uh, of the sequence, and that probability can be divided into components based on the context. And then, of course, we can simplify that context by using various assumptions. So we can say it is either unigram, which means that there is no context, bigram, which means that we are considering one word previously before a given word or before a predicted word. So trigram would be three words in all, 2 grams as the context, two words as the context, and one word that is predicted, and so on. So in particular, so depending on what n is, so you have the simplest one is of course the unigram, and then you have the bigram and the trigram, and in general you have n-gram. And this gram basically refers to the n basically refers to the total number of words in the context window. So we are predicting the next word given n minus 1 preceding context words. So in the unigram, the total window size is 1, so there is no context word. So the bigram model is also a Markov chain in probability theory, or a discrete state Markov process. So, and this is, if you're using an n-gram language modeling, this is quite commonly used in applications. The bigram is simpler, and for applications that can work well with this simple model, we go ahead with using this model. So last time we also mentioned how we can estimate the bigram probabilities, and the common estimation that comes from machine learning is the maximum likelihood estimate for a probability, let's say uh, W2 given W1 or Wn given Wn minus 1. We said that the maximum likelihood estimate of this is simply the count of W1 and W2, the co-occurrence of these two words, W1 followed by W2, divided by the count of the context, which is W1. All right. So this is the maximum likelihood estimate. And where do we get this estimate? From running text for that particular language. Okay. So if we have a large corpus, from that corpus, we will count the number of times that we see W1 followed by W2. So that would be numerator. and then we will divide it by the total number of times that we see W1 in the corpus. And of course, the total number of times that we see W1 is also equal to the total number of times that we see W1 with some other word W2, whatever that word is, W2. So this is the estimate of this probability. So let me go to the slides. So this is a very small example, just to illustrate how this probability is estimated. So let's say we have a small corpus that consists of these sentences, 3 sentences, and remember in modeling, you can use tokens. And in this example, you see that we have used a token to denote the start of a sentence. So those tokens can also be used in language modeling. And in general, as we go to more complex language models, we typically use subwords as tokens. And those subwords can also contain punctuations. Okay, so that you can get a completely, you can model a complete language with punctuation. Of course, for that, you will need lots of data, as we will see shortly. So in this example, of course, we have used the token S and slash backslash S as denoting the start and end of a sentence in addition to the other words. So I am Sam. So that's the first sentence. So I am Sam. Sorry, Sam, I am. And then the final is another sentence. So let's say we want to find the probability of or estimate the probability of I given the starting token S. ठीक है? Probability of I given the starting token S. So what will we do? We will need to find the number of times that we see S and I in the corpus. So S is the starting token and I is a word. So how many times do we see S and I in this corpus? So you see it in the first sentence and you see it in the third sentence, right? So you see it here as well and you see it in the first. So you have two counts of S followed by I. The total number of times that you see I is what? You see it in all 3 sentences. So that would be 3 in the denominator. So for this very simple example, the probability of I given the starting token would be 2 over 3. Okay? So you can take any other combination and you can easily find or estimate the probability. Of course, this is for illustration purposes. For a large uh, data set, you will be computing these values, and those would be more representative of how language is used in running text. So we will look at this example. This is a Berkeley restaurant corpus which has comments made by customers regarding what kind of food they want to eat, which restaurant they want to go to, which restaurant they found good, and so on. So these are some representative sample sentences from this corpus. I think the corpus has over 9,000 sentences. And of course, the domain is restaurants and food and so on. So let's go to the next slide. So this slide shows raw bigram counts of a subset of this data set, the Berkeley restaurant data set, and you can see the counts that are observed in this data set. So 9,222 sentences we have some selected words in this table. The column represents the preceding word. The rows, the rows represent preceding words, the column representing the following word. ठीक है? So, for example, if you want to look for the sequence I want, you just look at the count of I want. I think I want is over 800, right? Is that right? Similarly, want to is also above 600. But if you look at some other combination, for example, if you flip want to and want, आपके वर्टिकल में 2 देखें और उस पे कॉलम में want देखें तो that count would be 0. So obviously in correct writing no one would write uh, the word would want to want and then to. Sorry, to and then want. And of course you can see other interesting combinations as well. So eat Chinese, that is kind of reflecting the percentage of people or reflecting the interest in Chinese food. So eat Chinese is 16. Chinese food is also a large number, I think 80 or so. So you can find all these numbers in this co-occurrence matrix, where, as I said, the rows are preceding words, the columns, and the next word. So given this matrix, of course, and given the formula that we saw before, you can convert it to probabilities, estimated probabilities. Okay, so which is given in the next slide. So these are the probabilities. ठीक है, तो probability का बाईग्राम probabilities का फॉर्मूला आपको पता है, where you normalize by the count of the context word, which is a single unigram that follows a given word, that precedes a given word. ठीक है, so for example जैसे हमने I don't know the exact numbers but I think if I recall, so let's say आपके पास I want to find a estimate of let's say want I. ठीक है, this is basically count of I want divided by count of I. And I think, I don't know the exact number, but I think usually it's numerator पे 800 something है, 820 something, 825 कह लें. Or total number of words I is over 2000, 2500. So this is the probability. Okay, yeah. So 800 divided by 2000, so 0.33. So the probability of seeing this, so seeing want after I is 0.33. And of course, you can compute this for all combinations. And as you will notice in the slides, of course, this is a subset of the words. You will still see in this small subset, you will still see that some probabilities are very low and many probabilities are 0. So the probability would be 0 if the bigram raw count is 0, numerator is 0. Okay? Because that particular combination did not occur in the corpus. Just like we saw in the previous slide, so to and want has a count of 0. Okay? While want to has a high count. All right. Any questions so far? So, so once we have the bigram probabilities, which, as I said, bigram model is also a Markov chain. So in other words, we have defined the Markov chain, which means that we have all the probabilities, the transition probability from one word to the next word. So given this bigram model, we can also find the probability of complete sentences. So remember in the last lecture, we said that a complete sentence, which is a sequence of words, can be broken down into components, which consist of bigrams. So if I want to find the probability of this sentence P, the probability of I want English food. So we also starting with the starting token and then ending with the ending token as well, just to denote that this is a complete sentence. So we will compute this probability by multiplying the probabilities of all the bigrams plus the unigram at the start of the sentence, which is the starting token. तो ये सारी कंपटीशन यहाँ स्लाइड्स पे दी हुई है. ठीक है. So what is the probability of I given the starting? Then go to the next word times the next word, English want. So food English and so on. So you get a very small probability. So why do you get a very small probability? Because each of these probabilities has a value of less than 1, between 0 and 1. So if you multiply all these probabilities, you will get an even smaller value. And which makes sense because this complete sequence of words is even more less likely to occur in running text as opposed to a sequence of just two words. Okay? So you can use a bigram model to compute the probability of any sentence, which is a sequence of words of any length. ठीक है. So, we have learned a language model on some corpus. So, language model incorporates a lot of knowledge. So, it is, you can say, a knowledge base or is a language resource. And that's why also it's useful in many applications. And modern day NLP, as you know, is based on language modeling. If you have a good language model, you can do almost anything. You can do classification, you can do summarization, you can do translation, and so on. So, what kind of knowledge does it represent? So, you have information about, for example, grammatical usage. So, for example, want or I want to. So, want and then followed by to. Want is basically a kind of verb, and to is a preposition. So, grammatical information is also captured. Uh, so there may be, and this would have a high probability. And the reverse of that, which was you flip the order, meaning that the word are to want, you will not find that in the corpus. So that means that incorrect grammatically. So that's one piece of knowledge, which is syntactic information of how language is written. So syntax can include usage of uh, uh, for example, punctuations as well as correct grammatical usage of words. Secondly, it tells us about the world or actually the domain that we are modeling. So in this case was Berkeley restaurant database. It's about people using or conveying their expressions about restaurants in the Berkeley area. It tells about how interesting a particular food type is. Eat Chinese, eat English food, breakfast, so on. So all of this is also knowledge that we did not know before, but once we learned the bigram model or language model, we were able to now infer, uh, for example, which food is preferred by the people in this database that are represented in this database. So that's world knowledge, and also uh, so, for example, which are they interested in dinner, lunch, breakfast, and so on, and which types of food they're interested in. So, all of these pieces of information you can extract or glean from a language model. So, in general, syntactic information, semantic information, uh, pragmatic knowledge, which is, you can say, knowledge of the world. All of this is captured in some way in a language model, and you can extract it, use it in your applications. As you noticed in the previous slide, if you wanted to compute the probability of a given sentence, you will be multiplying various probabilities together. And if the sentence is large, then the number of components will also be large. In general, by the way, the number of components would be equal to the number of words. So if there are n words in a sentence, then you will be, in general, multiplying n probability components. And large number of probability multiplying would give you very, very small values. So underflow का issue हो सकता है. So usually, since we are always doing, we are trying to do comparisons, so हम log लेके कर सकते हैं. If you take the log of the probability, then you get a value that is easier to compute and add and subtract. Okay, so if your ultimate task is just to do comparisons, then you can do it directly on the log probabilities. Okay, and that is, I think, the case in 95, even 99% of the case in machine learning. We don't really want the actual probability. And let's say if you do even want actual probability, सारी computation log में करने के बाद में बेशक आप anti log ले सकते हैं. ठीक है. So n-grams, as I said, bigram, trigram, and in general n-gram. So many people have developed various databases. So these databases are, many of them are freely available. This slide lists some of them. So for example, in the older days, I think 10 years from now, the Google n-gram n-gram database was the most popular, but there are many others now. I think last year Infinigram was one of the ones that was released on a large database. So these can be used in our applications. And of course, many of these databases can be accessed through APIs and libraries. So there are tools available out there. Uh, so this slide mentions, I think, two of them, but there are others as well. Okay. So now let's move on to how do we evaluate a language model in general. So this is not specific to n-gram language model. This is evaluation of language model in general. Okay. So remember, I think I mentioned this previously before as well. Evaluation is very important. Whatever model that you use, that is also important. But if you are not able to justify that your model is good, then it's of no use to others. So evaluation, everything what we do, we must evaluate it properly, robustly. So there are generally two ways of evaluating a language model. Remember, language model is usually a component in a larger NLP application. So, so language model may be used to, for example, develop your embeddings, for example, contextual embeddings, and then those embeddings are used in applications like summarization or classification and so on. So one way to evaluate language model is to compare the performance of those applications while using different language models. So let's say if you have two language model A and B, तो आपने language model A से classification की और language model B से classification की and then check which classification performance was higher. ठीक है. Similarly, let's say आपने summarization का आपका task है, let's say या translation का task है, तो language model A से आपने translation की, B के साथ की. If B did better job at translating, then we would say that B was a better language model, although we evaluated it based on machine translation. So that's why this is called extrinsic or in vivo evaluation. So this is sometimes done, but it's less common. We would prefer something that is in vitro. We want to actually evaluate a language model directly because, as I said, it's a usually a component of a larger application. So if you are able to determine whether a particular language model in general is better than another language model, so we use it in all other applications, irrespective of whether it performs better in that application or not. So that's why in vitro, intrinsic evaluation is generally preferred. ठीक है? So in and of course, obviously, you are evaluating if you are evaluating your model using extrinsic model, extrinsic evaluation, you will be evaluating using an application that's usually time consuming. It's like a wrapper method. Run the language model over the entire pipeline and then get the results. So the intrinsic evaluation is usually done using the measure that's called perplexity, which we'll discuss shortly. And this is not a very fancy measure. It's actually probability. And as we'll see, it's just a probability that we can understand in a more meaningful way uh, because probabilities numbers can become very small. So using perplexity, you get a measure for a language model directly. If you have a language model A and a B and a C, the perplexity would tell us which language model in general is good. And if one is better than the other, then you can use that in all your applications. Of course, for different applications, there might be slight differences. But if you really want to determine the best for a particular application, then of course you'll have to do extrinsic evaluation that we saw in the previous slide. So this is kind of a refresher of your machine learning. So in general, and of course, if we want to highlight this much more for NLP, so we need to have a training set and a test set. So the language model is learned on a training set, meaning all those probabilities that we saw, the bigram probabilities, should be learned on a training set, and the evaluation should be done on a test set. And the test set should be independent of the training set. Otherwise, you will be biasing your results. So the idea, of course, again from machine learning is that once we have built a model from a training set, it should work for future usage. And future usage is best kind of approximated by taking a test set which is unseen, which is not seen or not available in the training data. So how do you choose the train and test set? Uh, this has to be domain specific. As we will see later on again today, if you choose a training set and then you apply that language model on a test set which is different from the training set, you will get very poor results. And let's say if you want to build a language model that would be applied to, uh, let's say the Pakistani context of, let's say, uh, Facebook messages, then you will have to collect a data set which is relevant to the Pakistani context of Facebook messages. ठीक है? So in other words, medical के ऊपर let's say करना है तो medical का data set होना चाहिए आपके पास. And then of course test it on the same type of data. If you test it on a different data, you will get poor results. Of course, nowadays we do have very general purpose models, the large language models that they are out there, but they have been trained on huge amounts of data. Okay? And in that case, of course, they are able to generalize in a much better way on different corpus. But even for those, there are issues. For example, जैसे उर्दू है या कोई और low resource language या पश्तो है या बलोची है, they will be very rarely captured in those databases. And if you try to use, for example, GPT and try to generate Balochi from it, you will get very poor results. Or try to understand Balochi from it, you will get very poor results because it has not been trained on such data sets. And obviously, as we saw before, the test set should be different from the training sets. Otherwise, we'll be biasing the results. So sometimes you also need a development set, which is sometimes also called a validation set. And in the case of language modeling, also we probably need a third set, which we call a development set. So this is the set on which we kind of tune our language model. ठीक है हम डेवलपमेंट सेट भी देख रहे होते हैं while we are trying to tune our model, but जब हमने फाइनल ट्यूनिंग कर ली है तो फाइनल इवेल्युएशन है वो टेस्ट सेट पे ही होगी, विच इज सेपरेट फ्रॉम बोथ द ट्रेनिंग सेट एंड द डेवलपमेंट सेट. ठीक है. सो ट्यूनिंग आप टेस्ट सेट पे नहीं कर सकते बिकॉज अगेन देन यू आर बाइसिंग योर मॉडल. So, so as I said, we will be using perplexity. So this is a measure that is used to evaluate language models. So if you have a good language model, then it will give a high probability to a sentence that is correctly written, of course, for a particular domain. ठीक है, and it will give a low probability to a sentence that is incorrectly written. ठीक है. So that is natural because but that's by definition. So that's what a language model is. So actually we are kind of using the definition of language model to define a measure which we call perplexity. So in other words, so if a language model is better able to predict the upcoming word, or as we saw in the previous case, better able or give higher probability to uh, correctly formulated sentences, then that's a better language model. So which basically means that on the test set, we compute the probabilities. And if the probability for for one language model on a given test set is higher than the probability for the second language model on the same test set, then we say that the first one is a better model. But if you recall in the previous slide, we mentioned that if you have a large sequence of words, computing probabilities would give you very small values. You typically will be multiplying a large amount of probabilities, and multiplying them will give you a very small number. Even if you take the log, then you still may have run into issues. And secondly, you since test sets may be of different lengths, let's say if you want to compare across test data sets, maybe एक test data sets में 1000 words थे, दूसरे में 2000 थे. So we want a measure that is kind of normalized to the length of those test sets. उसमें हम so the measure that we get is what is called perplexity. Okay. Okay, so perplexity and of course probability. So let's say we set the probability of sequence of word W. So this is what a language model gives you, an estimate for a sequence of words W. Of course, W can be one word or it could be 1000 words or whatever. So we say that W, let's say the text corpus of multiple words. So perplexity essentially is perplexity of some corpus W is basically the probability of W raised to power of minus 1 over n, where n is equal to the number of words in W. ठीक है. So this is called the perplexity. So essentially, it is the inverse of the probability on the test set as defined by the bigram model that you learned of the training set. And then you normalize it by taking the nth root. माइनस जो है वो इन्वर्स दे रहा है, वन और nth रूट दे रहा है. तो आपका जितना ज़्यादा लंबा कॉर्पस होगा उसका nth आप ले लेंगे रूट, एंड दैट विल गिव यू अ परप्लेक्सिटी. ठीक है. सो परप्लेक्सिटी, so by the way, in terms of probability, let's say you have a corpus W. Okay, let me write it in this way. Let's say आपके पास दो लैंग्वेज मॉडल्स हैं, P A, उसकी ये प्रोबेबिलिटी है. लेट्स से इसको मैं A कह देता हूँ, और P B W की ये प्रोबेबिलिटी है B. So which one would be considered better depending on the values of A and B? Obviously this is straightforward, right? जो मॉडल W को ज़्यादा प्रोबेबिलिटी देगा वो मॉडल बेहतर है. ठीक है ना, A या B. So if B is greater than A, then language model B is better. Since now we are taking the inverse, then PPP would be higher. PP of B of W would be greater than PP of A of W. ठीक है. And this number would be greater than 0. ठीक है. A higher perplexity means that the model is not good. A lower perplexity means that a model is good. एक सेकंड, ये क्या लिखा है. उल्टा होगा फिर, राइट, लेस होगा. सो प्रोबेबिलिटी बी की ज्यादा है तो परप्लेक्सिटी की बी की ज्यादा होगी. ठीक है ना, इट्स द इनवर्स. सो लोअर पीपी इज कंसिडर्ड बेटर. ठीक है. A higher perplexity is considered worse. All right. So essentially, that's what perplexity is. So now let's move on to some issues in estimation. ये वही सारी चीजें चल रही हैं. So this is the perplexity, the inverse probability of the test set, of course, normalized by the root of this length of the test set. Uh, so this is actually an intuition. You can look this up. If you have a lower probability, it means that the probability variation. If you have a lower perplexity, which means a higher probability, it means the probability of the sentence is high. So you can think in terms of okay, the number of variations for that is low. Okay, this is what is mentioned in this slide. आपके पास ज़्यादा चांस है कि एक ही चीज़ आएगी, ज़्यादा चीज़ नहीं आएंगी, because you have a higher probability or a lower perplexity. So this is some example on the Wall Street Journal corpus, which is a corpus of Wall Street Journal, which is a corpus of articles or news articles from this magazine. ठीक है. So you notice that Unigram has a perplexity of over 900. Bigram 170 हो गया. ट्राईग्राम 109. ठीक है. सो एज द मॉडल लेंथ इज इंक्रीजिंग, एनग्राम ट्राईग्राम है, तो आपकी परप्लेक्सिटी कम हो रही है. ऑफ कोर्स वी हैव ट्रेन्ड ऑन द वॉल स्ट्रीट जर्नल एंड वी आल्सो टेस्टेड on the Wall Street Journal, some holdout corpus of the Wall Street Journal. ठीक है. So this also shows that a higher order language model is a better language model in general, as long as you are testing on the same type of data. ठीक है. परप्लेक्सिटी उसकी कम हो रही है. Okay, now let's move on to sampling. Uh, so you have a language model. Can you use that language model to generate new sentences, right? Because remember, a language model is a generative model, a probabilistic generative model, and you can use it to generate data that looks like the original data from which you have learned that model. तो generative models यही होते हैं, and machine learning में भी आपने पढ़े होंगे. And language generation is a key key task or key component of any application in NLP. So language generation आजकल तो खैर almost universal हो गया, because we have large language models. हर चीज़ हम generation से करने की कोशिश कर रहे होते हैं. So we want to generate language. ठीक है. So how do we typically generate a language given a language model? So that's what we are going to discuss here. Uh, I can use the slides or okay. So okay. So Claude Shannon, of course, for those who follow history of science, may know this person. So this person is sometimes called the father of information theory, mathematician, electrical engineer, computer scientist. सारी चीज़ों में ये है. And he also worked in a little bit of linguistics and language and computer science. So, so these are some words that Shannon sampled based on his model, and how he did it is actually represented in the next slide. So basically, essentially, you so let's say you have a book which is your corpus, and let's say you want to sample words from that corpus. So what do? You flip pages randomly, select one word. एक word आपने select कर लिया. So that is your first word. Then you again flip pages randomly and then see on that page where does that word occurs randomly. जहां भी वो वर्ड उसका अकर करता है, उसका जो नेक्स्ट फॉलोइंग वर्ड है वो आप आउटपुट कर देंगे. ठीक है. तो आपके पास दूसरा वर्ड आ गया. ठीक है. सो नाउ यू हैव ए न्यू वर्ड. सो लेट्स से पहला वर्ड W1 था, दूसरा W2 था. अब आपने फिर फ्लिप किए पेजेस, W2 ढूंढा, डब्ल्यू एक नए पेज पे आ गए, उसमें देखा W2 कहाँ आ रहा है रैंडमली अगेन. और उस W2 का जो भी नेक्स्ट वर्ड था W3 लेट्स से, वो आपने जनरेट कर दिया एंड सो ऑन. So in this way, you will be able to generate your text given a model. So now actually we have a probabilistic model. So उसको हम किस तरह करेंगे? So this is basically called random generation. So so for a so this is actually a graph for unigram. So let's say you have a distribution for unigram words, okay, meaning the single words. The probability of let's say to, want, and so on, क्या है? And of course, all of these probabilities should sum to one, right? So how do you sample from this distribution? You generate a number between 0 and 1 and see in which component or which interval that number arises. And देखें कि वो interval किस word को represent कर रहा है. इफ इट इज रिप्रेजेंटिंग ए पर्टिकुलर फॉर एग्जांपल वर्ड वांट, तो वांट आप जनरेट कर देंगे. देन यू जनरेट ए न्यू रैंडम नंबर यूनिफॉर्मली बिटवीन 0 and 1. ठीक है. अब वो देखें वो किस इंटरवल में आ रहा है, और उस इंटरवल का जो वर्ड है वो आप जनरेट कर देंगे, एंड सो ऑन. So let me maybe give you an example which is smaller. Okay. तो लेट्स से हमारे पास बहुत छोटा सा एक 4 वर्ड्स का यूनिग्राम कॉर्पस है, या इट कुड बी हायर ऑर्डर ग्राम एज वेल, एज लॉन्ग एज यू हैव ए गिवन वर्ड. सो लेट्स से मेरे पास आई है, वांट है, और टू है. तीन ही कर लेता हूँ मैं. ठीक है. तो लेट्स से आई का प्रोबेबिलिटी 0.5 है, वांट की प्रोबेबिलिटी 0.4 है, और इसकी 0.1. ऑफ कोर्स ऑल ऑफ दिस सम्स टू 1. ठीक है. डिस्ट्रीब्यूशन 1 होनी चाहिए. सो नाउ यू हैव एन इंटरवल फ्रॉम 0 to 1. अब 0 to 1 में फ्रॉम इंटरवल 0 to 0.5, ये इंटरवल जो है ये वर्ड आपका किसका है, ये आई का है. ठीक है. एंड देन 0.5 प्लस, स्टार्टिंग फ्रॉम 0.5 ऑनवर्ड टू 0.9, ये वांट का है. ठीक है. एंड देन फाइनली 0.9 से आगे स्टार्ट हो रहा है टू 1, ये आपका इंटरवल 2 का है. ठीक है. So now given a uniform random generator between 0 and 1. ठीक है. यूनिफॉर्म रैंडम नंबर जनरेटर, लेट्स से मैं जनरेट करता हूँ, आई गेट 0.25. तो दिस वुड मीन दैट आई एम जनरेटिंग द वर्ड आई, बिकॉज इट फॉल्स इन दैट इंटरवल. सो लेट्स से फिर मैंने इसको जनरेट किया, तो आई गेट 0.95. इट मीन्स दैट आई एम जनरेटिंग द वर्ड टू, एंड सो ऑन. ठीक है. So this number that's generated, random number, this is generated uniformly, but then we check the interval in which it lies and generate that word. This interval is based on the histogram or the PMS, probability mass distribution of the words that we have. ठीक है. Similarly, of course, I have written that in terms of unigram. Let's say a given context मेरे पास the start of sentence. Let's say uh, so so let's say context. Let's say context S है. But then, of course, for this context, in other words, I'm trying to find the probability of I given S, probability of want given S, probability of टू given S. और वो probability वही हो सकती है या कोई और हो सकती है. जस्ट टेक एन एग्जांपल 0.4, 0.4 एंड 0.2. इसी तरह इसकी एक आ, बनेगा PMS, probability mass distribution. यूनिट इंटरवल में आप इसको बना दें, एंड देन यू जनरेट अ रैंडम नंबर बिटवीन 0 and 1 एंड सी विच वन इज जनरेटेड. ठीक है. So in other words, just to summarize, how do we generate text given a language model? So you first generate the first token. So that first token can also be generated randomly. So generate the first token. So that could be based on the unigram probability. ठीक है. So, and then repeatedly repeat, generate the next word given the previous generated word according to the probability distribution. ठीक है. Randomly, just like we discussed before, and you can continue in this fashion until you want to stop. Let's say k words or sentence token. So remember हमने एक टोकन s का दिया था, एक टोकन \s का दिया था. तो लेट्स से इसी जनरेशन में \s आ गया आपके पास, इसका मतलब यहाँ आप रुक जाएंगे. ठीक है. So this is called random generation. इस रैंडम जनरेशन में थोड़ी सी हम चेंजेस ऑफन टाइम्स प्रैक्टिस में करते हैं. सो दिस इज कॉल्ड रैंडम जनरेशन. So one of the issues with this random generation is that these probability mass functions or distributions have usually a long tail distribution. What does this mean? Means few words have large probabilities. Most words have small probabilities. Meaning that वही जो long tail distribution या thick tail distribution, शुरू में बस थोड़ा सा पार्ट है जिसकी probability हाई है, बाकी सारी आपकी यूं करके long tail चली जा रही है with small probabilities. So उससे ये होता है कि you tend to generate words that are of high probability multiple times, and of course that is coming from the probability theory, but sometimes हम इसको change करना चाहते हैं in some controlled way. तो उसमें कुछ तरीके हैं. आई थिंक वी विल डिस्कस दोज लेटर ऑन एज वेल. स्लाइड्स में भी यहाँ नहीं डिस्कस किए हुए. They have discussed it when they discuss large language models. So I'll just write the names here. So temperature sampling, and the other one is top K sampling. Okay. So you can use this to ensure that you get a better uh, or more reasonable estimate generations. But of course, all of these also random. But random को थोड़ा सा मैंने tweak किया हुआ है. तो प्योर रैंडम वही जो हमने ऊपर डिस्कस किया वो है. ऑलराइट. ओके. Okay. So the previous slides, actually, I was not able to see that, but the previous slide shows a language model that has been generated, that has been learned from the writings of William Shakespeare. And then using that language model, they generated uh, sentences or language. And you have for unigram, bigram, unigram model से किया, bigram model से किया, trigram model से किया, and of course higher order like 4 gram से. If you look at the words that you find when generating unigram, तो वो दोनों words में दोनों link कोई नहीं होता, but those are usually very common words that are appearing in Shakespeare writing. जब आप bigram पे जाते हैं, then of course you see some connection, but of connections up to 2 words. Trigram में तो आपको longer connections मिल जाते हैं. And so on. But वो जो longer connections भी जो है ना, they kind of capture the writings of Shakespeare. ठीक है. So उसमें कोई unique phrases आप कह लें जो शेक्सपियर के हैं वो highlight हो रहे हैं. So Shakespeare's corpus में over 800,000 tokens हैं या words हैं, and unique words आपके पास over 29,000 हैं. ठीक है. 29,000 यूनिक वर्ड्स, मीनिंग दैट वोकेबलरी साइज है 29,000. अब इस वोकेबलरी साइज के बाइग्राम्स कितने बन सकते हैं? ऑब्वियसली 29,000 स्क्वायर. ठीक है. सो दैट्स गोइंग टू बी ह्यूज नंबर. अब उस बाइग्राम 29,000 स्क्वायर ह्यूज नंबर में only maybe a few of them are appearing in the data set. I think over 3,000, 300,000. ठीक है ना. Only 300,000 bigrams have non-zero values as opposed to the total number of possible bigrams, which is 29,000 raised to power of 2, which is a huge number. So this is an issue that would arise in language models, which we are going to discuss next, which is essentially a manifestation of overfitting. ठीक है. So if you learn a model on the Wall Street Journal, and then generate the sentences using that model, you get generated text that looks very similar to the Wall Streट जर्नल. ठीक है, तो यहाँ आपको 1 ग्राम 2 ग्राम and n ग्राम दिए हुए वॉल स्ट्रीट जर्नल, and you notice that these generated text snippets are different from those generated using the Wall Street, sorry, those generated using Shakespeare writing. So this is another example. So let's say these generations are done from different authors writing. Of course, you have learned the model first from those authors and then generated text. And you will notice that you can fairly confidently determine the uh, writer from the generated text. तो इसमें शेक्सपियर भी है, इसमें आई थिंक जेन ऑस्टिन है, इसमें वॉल स्ट्रीट जर्नल एंड सो ऑन. तो वॉल स्ट्रीट जर्नल में आपके पास फाइनेंशियल टर्म नजर आ रही होंगी. वॉल शेक्सपियर की अपनी एक स्टाइल है, उसमें रियल नेम्स हैं एंड सो ऑन. एंड जेन ऑस्टिन, आई एम नॉट फेमिलियर विद दैट, बट उसमें भी एक यूनिक करेक्टरिस्टिक्स आ रही हैं. ठीक है. So the summary, quick summary from or takeaway from this is you need to choose the training data that resembles your actual usage or application of your language model. If your training data is different from your actual usage domain, then you will get very poor results. But then, of course, we also need to improve our estimation. So actually, what this is highlighting is the issue of overfitting, which you might have studied in machine learning, meaning that the MLE estimate that we did, maximum likelihood estimate, has overfitted to the training data. So it has overfitted to training data, and it will always give good results for that same type of data. And if you slightly change the data test set, you will get poor results. तो perplexity आपकी वो ज़्यादा हो जाएगी. We want our models to generalize to more uh, types of data. For that, of course, you need huge amounts of training data, or you need to improve your estimation techniques, and that's what we are going to focus next. So if you recall, when we looked at the Shakespeare corpus, so Shakespeare only used 300,000 bigrams from a total of, let's say, millions and millions of possible bigrams. तो बाकी सारे जो 99% of bigrams were actually zero. Let's say आप जब टेबल बनाएंगे को occurrence का, vocabulary 29,000 इधर है, 29,000 उधर है, इसमें 99% of the cells will be zero. Only 300,000 of the possible 29,000 times 29,000 cells have a non-zero value. ठीक है? So zeros is a problem in language, and it's a bigger problem in language as opposed to any other application. You can also think of this as a out of vocabulary problem, although that is slightly different. But you can think of this as a ट्रेनिंग सेट में आपके पास वो बायोग्राम नजर आ रहा है, बट टेस्ट सेट में वो नहीं नजर आ रहा. ठीक है. So you can think of this as a OOV problem as well, but also this is also viewed in the context of generalization or overfitting. The training set में जो learn किया, it should give you some decent performance on a test set, but it does not because of this large number of zeros in it. So let's analyze what is the issue here. So the maximum likelihood estimation, as you may know from machine learning, does lead to overfitting, especially if your data set is small. And in our case, since we do have a large amount of zeros, and those zeros may appear in our test set, so generalization and overfitting is very much likely. So the intuition of, so one way of handling that is to get better estimates, and better estimates can be done through smoothing, and various techniques of smoothing are possible. So we'll discuss a couple of them here. Okay. Okay. So trying to, one approach is various techniques of smoothing. ठीक है? So the idea in smoothing is mentioned in that slide. वो slide थोड़ी सी image थी, वो पढ़ नहीं रहा था, so I'm going to explain it here. Um, so what is the idea in smoothing? So let's say if you have a few words, let's say मैं characters ही ले लेता हूँ, A, B and C, ठीक है? And let's say D. And इनके counts हैं आपके पास. And again, this is a toy example. So 2, 3, 3 and let's say 2. So 6, 7, 8, 6, 7, 8, 9, 10. So total count is 10. ठीक है? Let's say in the test set you have E and F also, or of course this training set में इनके count 0 है. ठीक है? So the idea in smoothing is that we have a distribution over those four words A, B, C, D. अब उस distribution में से कुछ हम PMS probability mass बाकी words को भी दे दें. ठीक है, जहाँ E and F है उसमें से कुछ निकाल के हम E and F को दे देंगे. ठीक है. सो इन दिस केस E and F को लेट्स से मैं दे देता हूँ 0.5 टोटल मैं दूंगा, तो द 4 है, लेट्स से दोनों को 1 दे देता हूँ. ठीक है, ऑफ कोर्स दिस इज जस्ट एन एग्जांपल. सो लेट्स से मैं E और F को कोई प्रोबेबिलिटी मास दे देता हूँ. सो दोनों को लेट्स से दे देता हूँ 0.25 या 0.5 एंड 0.5. ठीक है. सो इट मीन्स दैट प्रोबेबिलिटी मास या काउंट में 1 बाकियों से मुझे कम करना पड़ेगा, सो दैट माई टोटल डिस्ट्रीब्यूशन स्टिल रिमेन्स एज 1. ठीक है. सो उसमें फिर ए, बी, सी एंड डी में से आपने 1 कम करना है. एंड लेट्स से वी हैव 4 ऑफ देम, लेट्स से हर एक में से 0.25 मैं कम कर देता हूँ. तो ये 1.75 हो जाएगा, 2.75 हो जाएगा, 2.75 हो जाएगा, 1.75 हो जाएगा. ठीक है. एंड नाउ यू स्टिल हैव ए डिस्ट्रीब्यूशन दैट सम्स टू 10 काउंट्स और द प्रोबेबिलिटी इज 1. ठीक है. सो दिस इज द आइडिया ऑफ स्मूथिंग, वेरी इंट्यूटिव आइडिया ऑफ स्मूथिंग. आपने एग्जिस्टिंग प्रोबेबिलिटी मास में से कुछ मास निकाल के बाकियों को दे देना है. ठीक है. So इसमें the simplest technique is the add one smoothing, which is also called the Laplace smoothing. Laplace smoothing, by the way, the name comes from the fact that we assume that we use a prior which is Laplacian. Of course, ये probability theory में ज़्यादा डिटेल में जाते हैं, यहाँ we won't be able to do that. ठीक है. But उसका simple जो manifestation होती है, it's like adding one additional event for each observed event. So in our case, let's say हम बायोग्राम निकालना चाह रहे हैं, तो बायोग्राम लप्लास स्मूथिंग का, let's say add one smoothing of W2 given W1. This is an estimate, is simply the count of W1 plus W2 plus 1. हर इवेंट को हम एक एडिशनल हम ऐड कर रहे हैं. हर इवेंट का हम एक एडिशनल ऐड कर रहे हैं, इसका मतलब है कि हम जितनी वोकेबलरी है, हर हम मतलब हमारे पास था W1 के साथ हर W1 के साथ कोई भी अगर कंटिन्यूएशन उसके साथ वन ऐड कर रहे हैं, तो इसका मतलब टोटल नंबर हमारे पास जो वोकेबलरी साइज है उतने वर्ड्स ऐड कर रहे हैं, तो डिनोमिनेटर में मेरे पास W1 + V आ जाता है. So this is called add one smoothing, and this commonly used in machine learning, but unfortunately this is not very useful again for NLP. We Because we have so many probability masses to move from the known words to the unknown words, to the observed bigrams to the unobserved bigrams. ठीक है, उसकी वजह से हमारी वो डिस्टॉर्ट हो जाती है. तो यहाँ आपको एग्जांपल दी हुई है. So this is the Berkeley restaurant corpus, and this is showing the so this is the Laplace smooth bigrams. ठीक है. So the probability is using the Laplace smoothing. और previous हमने देखा था कि वो probabilities निकाली थी without Laplace smoothing. But just to check कि कितना issue आ रहा है, you can find the reconstituted counts and then compare them. वो actually next slides में है. मैं आपको actually फॉर्मूला बता देता हूँ reconstituted count का. So for a given bigram, let's say C W1 W2, ये काउंट है उसका. ठीक है. एंड हमारा जो ओरिजिनल एस्टिमेट है वो बेस्ड ऑन दिस काउंट है, एक्चुअल ऑब्जर्व्ड काउंट है. बट हमने लप्लास स्मूथिंग वो जो ऊपर फॉर्मूला निकाला तो उससे हमने लप्लास स्मूथिंग करके प्रोबेबिलिटी निकाल ली. सो कैन वी फाइंड इक्विवेलेंट काउंट फॉर दैट लप्लास स्मूथ probability? That's what we want to do so that we can compare counts. काउंट कंपैरिजन से आपको पता चल जाएगा कितना प्रोबेबिलिटी मास हमने ऑब्जर्व्ड काउंट से अनऑब्जर्व काउंट्स में मूव कर दिए. ठीक है. so let's let's say the count after applying Laplace smoothing is C star. ठीक है. इसका मतलब है कि C star divided by C W1, this is the Laplace smooth probability, right? C star divided by जो इसका यूनिग्राम probability थी CW1, this is the Laplace smooth probability. So we can find C star by simply multiplying the Laplace by the C of W1. ठीक है. सो इन अदर वर्ड आपके पास ओरिजिनल C W1 W2 था, और आफ्टर लप्लास स्मूथिंग आपके पास C स्टार आ गया W1 W2. एंड नाउ वी वांट टू कंपेयर के C1 और C2 में फर्क क्या है, एंड विच इज गिवन इन दिस स्लाइड हियर. Here. So this is where you see that I think the top matrix is the original counts and the bottom ones are the reconstituted counts. तो अब इसमें आप देखेंगे कि ऑफ कोर्स जीरोस तो आपके पास कम हो गए हैं, जीरोस में कुछ वैल्यूज आ गई हैं. ठीक है. जो जो सी स्टार है वो जीरो नहीं है अब. बट यू नोटिस जो पहले वैल्यूज थी उनको बहुत ज्यादा कम कर दिया हमने. सो वी हैव चेंज एक्चुअली द एक्चुअल कंपोजिशन ऑफ द डेटा by significantly changing the numbers. For example, अब ये ज़बानी एक दो नंबर्स मुझे याद हैं. फॉर एग्जांपल चाइनीज फूड जो बाइग्राम था, चाइनीज एंड देन फूड हैड ए काउंट ऑफ 82. So after you did Laplace smoothing on this corpus, the reconstituted counts of Chinese food, meaning that you have removed probability mass from this bigram to others that are 0, वो 8 बन गया. So 82 से 8 आ गए आप. Why have you been reduced? Because ऑब्जर्व्ड बायोग्राम बहुत थोड़े थे, अनऑब्जर्व्ड बायोग्राम बहुत ज्यादा थे. तो ऑब्जर्व्ड में से काउंट निकाल निकाल के अनऑब्जर्व्ड में से कुछ थोड़ा थोड़ा दे दिया. तो वो थोड़ा थोड़ा उधर दिया तो ये बहुत ज्यादा चेंज हो गया. So this basically highlights that add-one smoothing is not recommended for language modeling, and it is used in other machine learning tasks, let's say classification and other things, but not for language modeling. And one estimation is a blunt instrument. So what options do we have? We have we have a few other options. So which I will discuss briefly and then conclude. Of course, there are other options, but वो ज़्यादा detail जो part था वो हमने since this is less commonly used in practice, is only used for smaller applications. तो वो जो advanced topics थे वो हमने remove कर दिए हैं इस साल. पिछले year में हम discuss करते थे. So we are not going to cover that. But the simpler techniques, we can use add k smoothing, where k is a number in 0 and 1, meaning that rather than adding 1 as a unit for each bigram or for each event, we add a small fraction for each event. ठीक है, maybe 0.02 or 0.2, so that कि उसमें से आपके बाकी पे वैल्यूज कम जाएं. So add k smoothing का जो फॉर्मूला फिर हो जाएगा वो बेसिकली ये है, c w1 w2 plus k divided by c w1 plus k. ठीक है, where I've said k is less than 1. Obviously it doesn't make any sense to take k greater than 1, because 1 से ही हमारे पास इशू आ रहा है, तो हमको k less than 1 करना पड़ेगा. So usually k is a small value. ठीक है, so that's one way that you can do. The other one is what is known as back off. Back off में क्या होता है? It's very simple idea. So back off में ये है कि let's say आपके पास कोई आपने ट्राइग्राम निकालना है या बाइग्राम ट्राइग्राम निकालना है. लेट्स से आपके प्रोबेबिलिटी ऑफ W3, W2 एंड W1. ठीक है, इफ दिस ट्राइग्राम विच इज ऑफ कोर्स द काउंट ऑफ C, W1, W2 एंड W3, इफ दिस इज जीरो, इसका मतलब है कि ऑब्वियसली ये आप कंप्यूट नहीं कर सकते, जीरो आएगा. सो देन यू चेक फॉर द लोअर n gram, which is the 2 gram, W3, W2. ठीक है, जो बाईग्राम, लेट्स से ये भी जीरो है, देन यू जस्ट यूज द यूनिग्राम W3. सिंपली बैक ऑफ. लेट्स से आपने बाईग्राम कंप्यूट करना है, तो बाईग्राम आपको मिल नहीं रहा था, यूज द यूनिग्राम. बाईग्राम जीरो है तो यूज द यूनिग्राम. बट उसमें ऑफ कोर्स इशू ये आएगा, जब भी आप एक हायर ऑर्डर से लोअर ऑर्डर पे जाएंगे तो प्रोबेबिलिटी मास फंक्शन सम वन तक नहीं होगा. बट यूजली वी डू नॉट केयर टू मच अबाउट दैट. बट एक तरीका ये है कि वी जस्ट डिस्काउंट द लोअर बाईग्राम्स, मतलब एक एक फैक्टर से मल्टीप्लाई कर देते हैं. सो लेट्स से इफ ट्राईग्राम is not available, then use 0.7 multiplied by bigram. 0.7 is a discount. 0.7 is a discount factor. तो ये भी बाय द वे ह्यूरिस्टिक है, या टेस्ट सेट पे या डेवलपमेंट सेट पे आप निकालेंगे क्या फैक्टर होना चाहिए. द आइडिया इज दैट वी वांट टू मेक श्योर कि जो सारी प्रोबेबिलिटी शुड सम और टू वन और शुड बी क्लोज टू वन, बहुत ज़्यादा ना हो जाए. ठीक है, सो दिस पर्टिकुलर अप्रोच वेयर आप डिस्काउंट भी लगा रहे थे, समटाइम्स दिस इज कॉल्ड द स्टूपिड बैक ऑफ. ठीक है, सो so you can use this approach as well. And the final approach is called the interpolation or linear interpolation. ठीक है, सो लीनियर इंटरपोलेशन में क्या होता है कि लेट्स से आपने ट्राइग्राम निकालना है, तो सो व्हाट डू यू डू, लेट्स से ट्राइग्राम How do you estimate that? So we have a parameter lambda 1 times trigram, जो भी ट्राइग्राम आए मे बी जीरो भी हो सकता है ये, प्लस lambda 2 times bigram plus lambda 3 times unigram. तो एक लीनियर इंटरपोलेशन कर लें where sum of lambdas is equal to 1. So weighted combination of all the bigrams. So maybe lambda 1 को 0.5 देंगे, lambda 2 को भी 0.4 देंगे, lambda 3 unigram को 0.1 देंगे. And where do you find these lambdas? Again from the development set. Training set, development set and test set. Remember those three sets that we talked about earlier? तो ये वहां से निकलेंगे. So these are the three techniques that are commonly used in practice, or for application that are based on n-gram आप इससे estimate कर सकते हैं. Plus of course as we saw earlier, n-grams के models आपको readily available भी मिल जाते हैं web पे. So you don't need to do your own estimates. But of course they will be based on their own corpora. But if you want to estimate an n-gram model on a corpus that you have, a private corpus, तो आपको इस तरह की टेक्निक को यूज करनी पड़ेगी. ठीक है? So I think that brings us to the end of this section. And any questions? Any questions? So a reminder again, so on Monday, the following Monday, we will have a quiz. And I'm planning to start the quiz at the start of class. Okay? So, and then we'll continue our lecture. So the lecture will start at 2:25. The quiz will start at 2. Lecture will be 2:25. Okay? So, so in the next lecture, we will start talking about neuro language models. And then again, so for some, ordering is sometimes difficult in NLP because so many things are changing. I think after that, immediately I'll probably start with RNN and transformers, because we need to go to that before we need to talk about some additional applications. And then we'll come back to neural language models again as well, especially the large language models. Because large language models, modern large language models are based on transformers. ठीक है?
सर
So I
ये
think that
कौन
is
सा
all from
चैप्टर
my
है?
side. जी
बुक का
question?
कौन सा चैप्टर है? लैंग्वेज मॉडलिंग वाला चैप्टर कौन सा?
ये चैप्टर 3 है बुक का. And we have essentially covered the entire chapter 3. इसमें कोई ऐसा चीज हमने छोड़ी नहीं. स्लाइड्स मैंने अपलोड कर दी हैं. द स्लाइड दैट अपलोड आर ऑलवेज अ गुड मेजर ऑफ क्या चीज हमने कवर की और क्या नहीं कवर की, और उसकी कॉरस्पॉन्डिंग आप टेक्स्ट बुक देख सकते हैं, पार्ट दे सकते हैं. कई दफ़ा कुछ स्लाइड्स में, जैसे पिछले में लॉजिस्टिक रिग्रेशन में मैं कुछ चीज़ें डिलीट कर दी थी, जैसे ट्रेनिंग का पार्ट. सो दैट पार्ट यू डिड नॉट डू नॉट टू कवर, you do not need to cover in the textbook. ठीक है? Anything else?